my 6A32 project, I created a trajectory-optimized torque vectoring controller for a Formula SAE race car. MIT Motorsports builds an electric race car each year to compete in the Formula SAE competition. The race car uses controls to assist the driver in optimizing performance. A two-track vehicle model is chosen for this analysis. The state variables are the x velocity, y velocity, and yaw rate. The control variables are the longitudinal force on each tire as well as the steering angle. The idea of torque vectoring is that the force applied on the left and right tires are not equal. This creates a yaw moment about the vehicle, which improves cornering capability. A direct transcription trajectory optimization was created to find the U of t that maximizes speed in a transient corner. A transient corner means that you start from rest and end in steady state, all for a constant turning radius. These are the four constraint equations that the vehicle must follow: force balance, moment balance, and the radius of curvature. This optimization was run for 5 different radius of corners and produced the velocity profiles shown on the left. To make sure this was reasonable, the velocity profile was computed analytically for the simpler case of a constant coefficient of friction tire model. The shapes line up. This gives us confidence that the optimization converged to the correct solution. The goal was to use the trajectories generated by this optimal controller to gain intuition and inspiration in order to create a more simplified controller for torque vectoring that could be implemented on the car. Here, the control effort is plotted as a function of steering angle, and it is shown that there is actually a linear relationship for low steering angles. It had been suggested in the literature that a very simple way to make a torque vectoring controller is to set the control input proportional to steering angle, but I was honestly surprised by exactly how linear the solutions were. And so it seems that the trajectory optimization almost discovered this control algorithm on its own. Zooming in on the relevant portion of the plot, we see, however, that the slope of this linear relation is different for different cornering radii. For the simplified torque vectoring controller, the purple curve, the 12-meter radius relationship, was chosen because this is roughly in the middle of all the radii tested and is also a fairly representative radius based on common track conditions. This control algorithm was implemented and it produced the velocity profiles shown on the left. For reference, the optimal profiles are repeated on the right. We can see that they have very similar shapes and magnitudes, which is the first suggestion that this type of control law could be very successful. For a more rigorous comparison, the average velocity is plotted for the optimal controller versus the torque vectoring controller. We can see that in 2 instances, the torque vectoring controller is actually faster than the optimal controller. However, this is non-physical, and it's because the torque vectoring controller was run with a higher force limit than the optimal controller was. So we can imagine shifting the entire blue curve down by some constant to make up for this. And then we can see that the torque vectoring controller performs much better for the 10 and 12 meter radii than it does for the other radii. And this makes sense because the linear relationship that we chose was based on the 12-meter relationship. Overall, this indicates that a slightly more complex controller should probably be pursued, where the relationship of the controller is dependent on the radius. Nonetheless, this extremely simple controller gives highly promising results when compared to the optimal.